Hi, I'm Ryan Baker, and welcome to the second video of the second week of our class, where we're going to start our discussion of diagnostic metrics. With diagnostic metrics, there are different measures, different metrics, for different methods. Today we're going to focus on metrics for classifiers. Later this week we'll discuss metrics for regressors, and metrics for other methods will be discussed later in the course. So let's discuss metrics for classifiers. Accuracy is the kind of best known, the standard one you'll often see in older work. It's also one of the easiest measures of model goodness, and it's also called agreement when measuring inter-rater reliability. In the inter-rater reliability context, it can be thought of as the number of agreements divided by the total number of codes or assessments. There's general agreement across fields that accuracy is not a good metric. Why is that? Well, let's say that my new kindergarten failure detector, the model that tells you, is this kid going to fail kindergarten, achieves 92% accuracy. If we just look at that number, we declare victory because it looks really good, right? But in fact, if there's non-even assignment to categories, accuracy is going to do poorly. And in fact, there's almost always non-even assignment to categories, so accuracy usually isn't a very good metric. Imagine an extreme case. 92% of students pass kindergarten. Probably the case, right? How many kids really fail out of kindergarten? And I've got a great detector. My detector always says pass. No matter what the data is, if the kid doesn't show up to class one day, if the kid sets fire to the teacher, my detector says pass. Accuracy of 92%. It's right in the 92% of cases where students pass kindergarten. It's only wrong in the other 8%. So despite having an accuracy of 92%, my detector is completely useless, has no information at all. Another metric that we can think about that's a little better is kappa, also known as Cohen's kappa. Kappa is the agreement minus the expected agreement divided by 1 over the expected agreement. With kappa, you might be saying, how do you calculate that expected agreement? Where does it come from? Where it comes from is the base proportions of the two groups. So let me show a simple example. What we're going to do is we're going to say, let's take the proportion of students in each group, in each detector and real data, and let's say if students were randomly assigned to the groups, but in the current proportions, what percentage of time do we see agreement? So let's take the example of a detector that's detecting if students are on task or off task, with data that says on task or off task. What we can see is that 20 times the data and detector agree the kid's off task, and 60 times they agree the student's on task, and the other 20 cases they disagree. What is the base rate agreement here? Well, first of all, we can say, what's the percent agreement? The percent agreement is 20 cases where they agree and 60 cases where they disagree, for a sum total of 80 out of 100, 80%. What's data's expected frequency for on task? We're going to look at the frequency for both on task and the frequency for off task. Well, it's 75%. How do we get that? Well, we take the data and we take the cases where the data says on task. 15 plus 60. 15 plus 60 is 75. So in 75% of cases, we have the data expecting to be on task. What's the detector's expected frequency for on task? Well, look at the detector on task column. 60 plus 5 is 65, or 65%. What's the expected on-task agreement? Well, if we take the two cases and we say, what's the data's percentage of on-task, what's the detector's percentage of on-task, and we say there's actually no correlation between the detector and the data, we're just going to have people be on-task according to the detector or the data by complete chance according to the proportion, 75% and 65%. In that case, the expected on-task agreement is 65% times 75%, which is 48.75% for those of you who have a calculator in your head. So we can put that in the bottom right column. Now, what are data and detectors' expected frequencies for off-task behavior? To see those, we want to look at the detector off-task column and the data off-task row. What we get is 20 plus 15 is 35% for detector off-task, and 20 plus 5 is 25% for the data off-task. So what's the expected off-task agreement? It's going to be that 25% times that 35%, which equals, again, using your calculator in your head, 8.75%. So if we take these two, we can say we should expect agreement of on-task in 48.75 cases and agreement on off-task in 8.75 cases for a total expected agreement of 57.5%, or 57.5 cases in this very nicely set up example. So what is kappa? Kappa is the actual agreements minus the expected agreements divided by the total possibility of agreements minus the expected agreements. In this case, 80% minus 57.5%, over 100% minus 57.5%. So in other words, kappa is 52.9% or 0.529. So this model is 52.9% of the way from expected agreement to perfect. So is that any good? What do you think? So here's how you interpret kappa. If your kappa is 0, then your agreement's a chance. If your kappa is 1, then your agreement's perfect. If the data says something, your model's going to say exactly the same thing. If your kappa is -1, then your agreement's perfectly inverse. Whatever the data says, the model will say the exact opposite. That can actually kind of be useful in a weird way, but it's not really something you want. And if your kappa is greater than 1, you messed up somewhere. What if kappa is less than 0, but greater than negative infinity? In this case, this means your model is worse than chance. Now, people didn't really see this very often when they used to use kappa for inter-rater reliability back in the day. But you do see it more often if you're using cross-validation, in which case it means your model's junk. And what it really means is that your model goes in opposite direction in the training set and in your test set, which really is not something you want. I don't see it very often, but I have seen it in my life. What if kappa is between 0 and 1? Well, that's the hard case. What's a good kappa in that range? There's no absolute standard. If you've got a data mine model, typically 0.3 to 0.5 is good enough to call the model better than chance and go ahead and publish it. In affective computing, which is a really hard problem, lower is still often okay. And if you send something to certain conservative ed journals, then they're going to want to see a 0.9, which no one's ever seen for anything other than a completely well-defined construct where you defined everything down to the finest detail. Why is there no standard? Why can't people just say, yes, 0.4, that's my magic number, or 0.8, that really is what we should use? Well, in fact, people do often say 0.8, that's the magic number, you have to be above 0.8. The problem is that kappa is scaled by the proportion of each category. So you really shouldn't be looking for magic numbers because in fact kappa is influenced by the data set you're in. When one class is much more prevalent, expected agreement is going to be higher than if the classes are evenly balanced. So it's harder to get a good kappa in very imbalanced data. Part of the point of kappa is to deal with the fact that you have imbalanced data, but in fact it kind of biases against you when you have imbalanced data. The opposite of accuracy, which biases in favor. The biases of kappa are much weaker than the biases of accuracy. It's a much better metric, but it's not perfect.
So because of this, comparing kappa values between two data sets in a principled fashion is highly difficult. It is okay, however, to compare two kappa values in the same data set that have at least one variable in common. A lot of work went into statistical methods for comparing kappa values in the 1990s, and there was no real consensus. It turns out that there's just not a really good way to do it, so far as we currently know. Informally, you can probably compare two data sets if the proportions of each category are similar, whatever that means. So in other words, if you have two categories and in one data set it's 60%, 40%, and the other one it's 55, 45, you're probably okay. But you wouldn't want to compare 60-40 to 93-7.
So I hope you found this lecture on kappa and accuracy interesting. They're both measures that you'll see sometimes. Kappa increasingly compared to accuracy because it is a better measure. In the next lecture, we're going to continue with classifier metrics of goodness, including ROC curves, A prime, precision, and recall. So I'll see you next time. I'm Ryan Baker, and this is Big Data Education. Thank you very much.